Hello and welcome back. Today we're going to continue on computation and we're going to formally define NP, NP-completeness, and then start showing some actual mapping reductions. But remember, we are on Piazza, we are on YouTube. If you have any questions, go ahead and shoot them out there and I'll answer them as they come in. But remember last time we stopped off by I presented the idea of reductions by looking at some Python code, where you can, call you implement a function by calling another function, taking its results, and then manipulating those results. Those are generally referred to as Turing reductions. If you think of a function as a Turing machine, one Turing machine simulating another Turing machine is basically calling a subroutine, basically. We don't, however, want to abuse that power. We don't want to cheat by hiding the complexity in that sub function, right? If you were doing minimum spanning tree algorithm, and as a precursor to that, you had to sort the edges, like in in Kruskal's algorithm. Then you can't say that doesn't cost you anything, right? That there is a subroutine that is going to cost you n log n comparisons, and then you go on to analyze the rest of the algorithm, and if it's more, then so be it. Then there's a different elementary operation, but you can't just discount that, right? And we don't want to do the same thing when we're looking at our reductions. You don't want to basically abuse the reduction to hide the complexity. For example, I could write an algorithm for SAT, for satisfiability, right? Here's our input is a formula, or a predicate, P, right? And all I need to do is call my non-deterministic SAT algorithm that we already developed yesterday. Basically, again, you guess a formula, and then you verify it, and the machine itself, which I'm calling here NSAT, non-deterministic SAT, it magically determines that that there's one computation path that accepts, so the entire thing accepts. And if I just put that into a result and then return the result, or output the result, whatever, right? There's a deterministic polynomial time algorithm, right? But it is not, in fact, a deterministic polynomial time algorithm because I'm abusing this function call. This is sometimes called an oracle. You can like in Greek mythology, you could ask an oracle something about the future or something, and they would just magically tell you. Usually it came at a price, or with an asterisk, and led to tragedy or whatever. But here our oracle is, well, we'll just ask the oracle, and we don't know how it gets its answer. It's just magic, right? But we can't ignore the fact that is using non-determinism to get its result. So what we need is a stronger notion of reductions. We don't want to give that reduction the full power of non-determinism. We only want to use as much power as is in our algorithm itself, right? So here's the actual definition, and these are mapping reductions. So let P1 and P2 be problems. This is not P as in deterministic polynomial time. We say that P1 reduces to P2, and we write, as I was writing before, P1 is less than or equal to, with a subscript P there, a P2. If there exists, excuse me, give myself some more room. If there exists a function, f, such that f maps all instances of P1 to all yes instances of P2, no instances likewise. So in other words, it preserves solutions. Now, technical point here, it doesn't have to map yes to yes, it just has to be consistent. It has to be, like you could map yes to no and no to yes, like flipping the answer, but then at the end of the day, you could have just flip it again, and it would still be a reduction. It would still be preserving those solutions, those answers, excuse me. And f is computable by a deterministic polynomial time algorithm. That's where the subscript comes in right here. The subscript, we're saying that we're only going to use the power of polynomial time in order to do our reduction. We're not going to abuse a full-blown non-deterministic polynomial time Turing machine in order to hide the work and let it do our work for us. All right? Now, this allows us to define both NP and NP completeness. A problem is in the complexity class, NP, if it is decidable, and again, problem, language, same thing, by a non-deterministic polynomial time Turing machine. Just like that's the same definition of P. It's just that now we're endowing our Turing machines with the power of non-determinism, the power to guess a solution. You still verify it in deterministic polynomial time, and then the machine itself accepts if any computation path accepts. A problem is in the class NP complete. Or a problem is, let me just go ahead and not call it a class, but is NP complete. It is NP complete. If every problem in NP reduces to it. All right. What does that mean? So I drew this picture last time. Let me go ahead and go back and redraw it. We drew this picture last time of the complexity landscape that we're looking at. Oops. Where we've got all of NP here. Now, this is any problem that you can come up with a non-deterministic polynomial time algorithm or Turing machine to decide it. Within that, you've got the complexity class P, which is pretty much everything that you've looked at so far, at least that you've written solutions for. Minimum spanning trees, sorting, etc., etc. In order to establish a relative complexity, what we want to isolate what are the hardest problems, right? Again, if you want to look at this in hand-wavy kind of fashion here, everything going up is hard. Everything over here is easy, right? So that's why P is down here, NP is up here. Well, what's the hardest problem? What's the upper echelon of NP problems? We call that NP complete problems. Now, the way that we've defined it is we've said that every problem in the entire NP landscape, including other NP complete problems, reduce to it. And again, reduction is not as in like it's reducing the complexity or lessening the complexity. In fact, the way that I've drawn it here is that things going up, it's more difficult. They're harder problems. And so the hardest of the hard problems up here are NP complete problems. And in fact, they're all equally hard from the view of NP completeness because everything reduces to this problem. Therefore, if you're in NP complete, they reduce to each other. It kind of almost defines an equivalence class of problems. Okay. Why do we do this? Well, first of all, we need our first NP complete problem. In fact, from this is due to Cook, Levin. The SAT problem is NP complete, and I'm not going to go over the proof here. Basically, they came up with what's called a canonical language. Given a machine M and an input X, the language would be M is a non-deterministic M accepts. M is a non-deterministic Turing machine that accepts X within a polynomial number of steps. That's like by definition that's going to be a complete language. So what they came up with was a reduction from that language to SAT, satisfiability, by simply just taking that idea and encoding it as a bunch of ands, ors, disjunctions, conjunctions. The computation of the non-deterministic machine itself was encoded as a circuit, basically. That circuit then can be expressed as a satisfiability formula. Does there exist a computation path that accepts because m accepts x within a polynomial number of steps? Again, we're not going to go into that level of detail. We're going to start out from the basis that SAT is the NP complete problem that we're going to start out with. So why is this important? Why is this useful? Right. It gives us a framework for establishing the relative difficulty of problems. Right? If we can show that something is NP-complete, that means that or by taking an NP-complete problem and reducing it to that problem, again, going up harder and harder and harder, then we've shown that that problem is indeed very, very difficult. And nobody knows how to solve it in a polynomial amount of time. Not only that, but showing. So let me go ahead and write that down. Showing that a problem is NP complete gives you evidence that it is very difficult. Right? And to solve it, you should look at heuristics or other methods, right? Difficult, sorry, there we go. So don't even bother with a brute force method, right? Immediately go and start looking and seeing if you can estimate things, or maybe it's an optimization problem, the 0-1 knapsack. Maybe you'll showing that that's NP complete means we're not even going to try to solve this exactly. Let's go ahead and estimate by some greedy solution, and then we can prove that that greedy solution is within 1/2 of the optimal solution, right? Some heuristics like that. Being greedy is not going to give you to a globally optimal solution, but it'll still lead to a solution that's probably good enough. In fact, what's the old saying? What's better than good? Good enough, right? All right. So another reason is it gives us a way to understand P and NP. Why? If we can show even one polynomial time algorithm for one NP complete problem, then we've collapsed the entire landscape. All right. Now, what do I mean by that? Let's go back to our picture here. Now, imagine that it doesn't matter. Let's go ahead and take SAT. Suppose that I were, doing lots of research here, and I were able to, and I would actually come up with an algorithm A that solves SAT, satisfiability, in polynomial time, in deterministic polynomial time. That means that any problem in this entire landscape can be solved in polynomial time. Can be solved in polynomial time. Why? All you have to do is our trick that I demonstrated yesterday. Function calling function calling function. Algorithm calling algorithm as a subroutine. Take any problem over here, reduce it to SAT, right? And now solve SAT, and that gives you an answer to the original. Right? Again, all these reductions are going up. Right, and that they're not necessarily harder. They are, remember, that's why we use less than or equal to, because we don't know if they're strictly harder. Nobody knows if this landscape collapses down to P. P, are they equal or are they not equal? Most people are going to be in this camp. And even the people that think that P may be equal to NP, they usually come up with a caveat that the reduction itself would be so large, like say n to the 100, that maybe that for all practical purposes, these problems still cannot be solved on today's machines because as we've seen before, n squared is even not really practical from most point of view. Even an input size of 1 million or something, it's going to take weeks, months, years, centuries to compute these things. Okay. All right, so that's why we like looking at these things. So how do you go about proving them, right? And for that, I'm just going to cut and paste this 5-step process. I believe that this 5-step process is can be credited to a book. It's a compendium of NP-complete problems. Forgive me for not having the authors memorized. I should, but if anybody knows, go ahead and put it in the chat. But there's a 5-step process here. You want to show that some problem P, and note here that it is scripted P. That's not polynomial time. That's why I'm using different fonts to denote these things. Suppose that we want to show that a problem P is NP-complete. Well, first of all, you got to show that it's in your landscape. You've got to show that it's an NP. That's pretty easy by simply coming up with a non-deterministic polynomial time algorithm to solve for it. And again, that's easy. All you have to do is guess a solution, come up with a deterministic polynomial time algorithm to verify the solution, and show that both the guessing phase and the verification phase operate in polynomial time. 2, you select a known NP-complete problem to reduce from to your problem. Remember, we're not reducing down. Reductions generally go up. If you reduce down and show that an NP-complete problem reduces down to a polynomial time problem, then you've basically shown a polynomial time algorithm. Take SAT, reduce it to minimum spanning tree. That's insane, but suppose that you were able to do it, right? Then that would collapse the entire landscape down to P. So you need to select a known NP-complete problem to reduce from to your problem, establishing that relative complexity. Now, by symmetry, of course, and definition, your problem would also then reduce to that NP-complete problem, because every NP-complete problem reduces to every other NP-complete problem by definition. Right? 3, you come up with a mapping reduction, like we just defined, that maps yes instances to no instances. And so we'll understand this idea of a mapping reduction as we take a look at a couple of examples. Then you need to prove that your reduction is correct, that it preserves solutions, so that when I reduce one NP-complete problem to another problem, yes instances down here are preserved to yes instances up here. No instances down here are preserved, no instances up here. Usually that's by exclusion, though, right? Yes, if and only if yes. By exclusion, no, if and only no, if no, so you don't have to take care of that second step. Then finally, you show that your reduction is computable in deterministic polynomial time. Okay? And again, that's easy. Usually these things involve what are called gadgets. That's the first one that we're going to look at, actually. We're going to reduce from SAT, which is our first and only known NP-complete problem, at least in this course. There are hundreds of NP-complete problems. And we're going to reduce that to another graph problem. So a problem about logic can then be recasted as a problem about graphs. And you'll see that this is actually quite common, right? So we're going to show a reduction from SAT, a known NP-complete problem, to click. And hopefully you remember the click problem. That's a graph problem where you have you're trying to find a click of a certain size, a maximal click, but the decision version is, suppose that you've given a graph and an integer k, right? You want to show that there is a click of size k. A click is a bunch of vertices that are all connected together, right? So here's the definition. Or here's our 1, 2, 3, 4, 5 step-by-step process. So we're going to show that the click problem, again, given a graph G and an integer k, does G have a click of size k or not? We have to show, one, that that's in NP. Okay? So let's go back over here. And here's my non-deterministic algorithm. Oops. Non-deterministic algorithm. for click. All right? My input is going to be a graph g equals v comma e and an integer k. And I won't bother with the output here. The output is going to be, well, here, I will be. Output will be, I think we have, yeah, we've got plenty of time. Yes, if g has a click of size k. No otherwise. All right? To show that this is an NP, again, you have a guessing phase. 1. Guess a subset C of V such that the size of C is equal to K. Right. 2. Verify. Right. So all we need to do is look at all pairs. For each pair, U and V, in that subset, I'm not looking at all vertices now, I'm only looking at this supposed click here. If U, V is not connected, is not in the edge set, then reject. Right. Otherwise, at the end, we accept. Because we found a subset of size k such that all the vertices are connected by an edge in the edge set. And so we end up accepting them all. And again, this is done by magic, right? We're not randomly generating a subset of size k. We're not looking at all subsets of size k. We're not looking at them all in parallel in one massively parallel operation. We are magically guessing a solution, and then the non-determinism, well, the real non-deterministic magic is that if there is any computation path in this entire thing that accepts, then the entire machine accepts, the entire algorithm accepts. So all we have to do is show that this runs in polynomial time to establish that it's an NP. Well, this one is going to be order k, right, which is at most order n. If you're looking for a maximal click, the maximum that a click could be would be all vertices, which would be a complete graph, and so k is bounded by n. This verification here is going to be order k, choose 2, right? Which again is bounded by order n choose 2, which is going to be n squared, right? And that's the verification phase. So this operates in polynomial time and linear time. This operates in quadratic time. So the entire thing operates in polynomial time. But this guessing phase, this guessing phase right here is hiding the real work behind its non-determinism. Okay. All right. Now we're going to select a known NP-complete problem to reduce from. And that's I mean, I already set us up for that. Generally, this is more of an art that you have a problem. You look for a similar problem in the compendium book with hundreds of different NP-complete problems and say that my algorithm, my problem looks kind of like that one over there. So let's go ahead and try to reduce from that one to my problem and see if it works. If it didn't work, okay, I'll select a different problem or something like that. But I'm giving that to you. So we're going to reduce from SAT. In particular, we're going to reduce from a special version of SAT, which is called 3CNF. I think we've covered that before. But if not, that's all right. Let's remind ourselves what it looks like. It looks like this, where it's 3CNF. It's a conjunctive normal form. So each one of these things is a clause. Right? A clause has at most 3 variables. That's where the 3 comes in. And each clause the conjunction is taken. That's where conjunctive normal form comes in. And then each clause itself is only ors of either the variable or its negation. It's pretty easy to show that using logical equivalences that you can take any formula and you can get it into 3CNF, a third conjunctive normal form. by introducing dummy variables, by factoring things out. Basically, it's kind of like algebra, where you could, factor things out. You could take all of your negations and make sure that they're factored out, so that that you don't have a negation of a clause itself. The negations are only on the variables themselves. That you collect disjunctions, so that you only have conjunctions outside. Right? That's third normal form. We'll come back to this here in a second. Okay. 3, we define a reduction, a mapping reduction. So in other words, given a 3 Cnf formula, we're going to have to transform that into a graph. Right? Given a 3 Cnf formula, we want to produce a graph such that the formula is satisfiable if and only if, again, we need to preserve solutions, the graph has a click of a certain size. Okay. Why, again, this is a reduction. We're taking sat and we're reducing it to click. Reductions go up visually. It's harder, right? Or at least as hard is what you really want to call it. So that if you had a solution for click, then you would have a solution for sat, right? And here's our reduction. Again, these things involve usually they involve coming up with a gadget or something, and I'll show you what the gadget here is in a second. So given a 3 Cnf formula, suppose it has the following clauses. There we go. Given a 3 Cnf formula with k clauses, right? You can always manipulate that so that you have exactly k clauses, or you just change your k, right? If it had 10 clauses, then we're going to have k is equal to 10. If it has 3 clauses, then k is equal to 3. With each clause having 3 variables or their negations. You can have exactly 3 variables by simply introducing dummy variables into the equation that can then be thrown out in the final in the final evaluation of it. Right? We're going to create a graph G as follows. Right? There will be 3k vertices, 1 for each literal in each clause. It doesn't matter if the literals are repeated. If I've got x1 over here and x1 in some other clause, it's still going to get a unique vertex. Okay? The edges will be drawn as follows. We'll draw an edge between 2 vertices if 1a, they are in different clauses and are b, consistent. Consistent means that they are not the negation of each other. Right? So those are our 2 conditions, A and B. In fact, I'll put those on their own lines here, A and B. All right, the markdown's not going to let me do that. If I go period. Nope. Okay, fine. Like that. All right, bullet pointed instead. They are in different clauses and are consistent. All right, so what does that look like? So let's go back over here just to show you an example. Here is a 3 Cnf formula. K, of course, is 3. It has 3 clauses, 1, 2, 3. Each clause has 3 literals or their negation, and it's in conjunctive normal form, ors and ands outside. Okay? We're going to draw a graph according to those 2 rules. Now, first of all, every literal or its negation will get a vertex. And so we'll end up having 3 times 3k vertices, or in this case, 9 vertices. So I'm going to go ahead and look at clause C1 over here, C2. Let me label them so that you don't lose them. C1 over here is going to have 3 vertices. x1, negation of x2. I'm just labeling them so that you see how this map works. Oops, sorry. There we go. C2 will have x1. Remember, it's repeated. Even though x1 was over here, it's going to be repeated over here. It's repeated over here. It's the same variable in the original formula, but they're going to end up being different vertices in the mapped graph, in the graph gadget here. negation of x2, it's exactly the same, and negation of x3. There we go. And then finally C3 over here is, what do I want? X1, X2, and X3. There we go. Now the second part is where we draw edges. We're going to be drawing edges if they're in different clauses. So in other words, I'm not going to be connecting anything within a clause. I'm only going to connect from this clause to that clause, this clause to that clause, and maybe this clause to that clause. But I'm not going to connect anything within those clauses. The second thing is that they have to be consistent. There can't be the negation of each other. So for example, let's go ahead and go with, this is x3 right here. There we go. Let's go ahead and start with this clause over here. I'm going to connect it to, how do I connect it to this clause over here in the graph? Well, x1 will be connected because they're consistent. This is not the negation of this original one over here. So I'm actually going to end up drawing a lot of edges here because that's negative x2 is not the negation of x1. Likewise, the negation of x3 is not the negation of x1. So I end up drawing all three over there. Negation of x2 will also go to all three. x3 will go to x1 and x2, but be careful, right? Do we go from x3 over to the negation of x3? No, those are not consistent. This is x3, a literal x3, and this is the negation of that literal. So I do not draw that edge. Okay? Now let's go ahead and take care of the first clause with this clause over here. Again, x1, x1, x1 to x2, x2 to x3. x2 will be connected to x1, and negation of x2 will be connected to those two. But once again, the negation of x2 and x2 over here will not be connected because this is the negation of that one. x3 will also be connected to all three. There we go. Now, the only other edges that I need to draw are between this clause and this clause over here. x1 will be connected to all three. Right. So this is getting very, very messy. x2 will be connected to all, just the first and the second, because x2, negation of x2 and x2 over here, they're not consistent. Right. And then finally, x3 will be connected to the first two, but not the last one because those are negations of each other. Right? Now, I need to show that this is actually preserving solutions, which we'll do formally here in a second. But just to show you why, we'll come back to it. Okay. Let's go ahead and go back to step 4. Right? We don't have to prove anything yet. Right? Coming up with these things, of course, is a lot of work. You have to try a bunch of things. It's like any proof. You have to try a bunch of things until you find something that works. Right? And so how did somebody come up with this? Well, they just tried a bunch of things until something worked, and then they proved that it worked. We're going to prove the reduction is correct. Right? That the formula is satisfiable if and only if G has a clique of size k. Right? Hold on, pause, and I'll show you here the idea here in a second. 5, let's go ahead and jump ahead though and show the reduction is polydeterministic, can be computed in deterministic polynomial time. Right? And that one's pretty easy, right? All you need to do is iterate over the clauses, right? We're outputting 3k vertices. Right? We're outputting at most, they'll end up being 3k, choose 2 edges. Is that gonna, nope. Oh, there we go. Which is are both are polynomial in n, right? In k, the number of clauses, right? Which is bounded by n, the number of variables. Right? And we can say that it's bounded by the number of variables because if you have too many clauses, then it becomes a trivial solution. If you have so many clauses that and they're not repeat, and some are going to be repeats. If they're not repeats, if there are repeats, you can throw them out, of course. But if they're not repeats, then eventually you'll get to a trivially satisfiable formula, right? So don't worry about that. The bounding is pretty clear. Right? So let's go back to number 4 here and argue that it is correct. Visually first, okay? So first of all, I'm going to say that this is satisfiable. Right? What variables or what values can we set these variables to get a satisfying assignment? That satisfying assignment will correspond to a clique of size k. Right? That's the magic here. So let's come up with something, I don't know. If we set x1, well, if we set x1 to 1, then we're already done. It doesn't matter what everything else is. 1 or it doesn't matter. 1, 1, they're all going to be true. Let's look for something a little bit more challenging, though. So let's say 0, or a little bit more interesting is what I want to say. That means that we would have to let's go ahead and make this third clause true by setting x2 to 1. Right? That makes the third clause true, but it yeah, we're sunk then. Yeah, we're not going to be able to do that. All right, we're not going to be able to do that because it'll make this third clause true. The only one that we have left to play with here is x3. And if we set it to true, that makes the first clause true. If we set it to false, that makes the second clause true. But then the other one is always going to be false. So let's go ahead and say 0. Oops. Right. That will make the first clause and the second clause true because by virtue of that negated literal there. And all we have to do is take care of this third clause, and so I'll set that to 1. There are a couple of other truth settings here that would actually work as well. Okay. Now, observe here that that is going to lead to a clique of size 3. Right? Why? All we have to do is take the variable that makes each clause true and look at its corresponding vertex over here in the mapped graph. So for example, the first clause, 0, true, this is going to be false, true, true. We can take either one. Let's go ahead and take x3 there, right there. Let me highlight it with a highlighter instead. There we go. Right. That one's true. Let's look at the second clause. So false, true, and then false. So this second one here will end up being true. And the third one is going to be false, false, true. So it'd actually be x3 again that gives us the truth, setting that this clause here to true. And all I need to do is observe that all of those are going to be connected by the definition of our reduction. Right? That this is going to be connected, that x3 and x3 are going to be connected. The way that we drew it was right here. And then finally, x2, the negation of x2 and x3 are also connected right there. Right? Unfortunately, I didn't highlight those, but you can see it's handwritten. There we go. Right? And that forms a clique. That's a clique of size k equals 3. So our mapping preserves solutions basically. Now, that's just one example, and that was me showing you what it looked like. If you want to do this more formally, of course, you would have to come up with a full proof, right? In fact, we can do that. Well, I mean, it's pretty straightforward. I don't want to beleaguer it, but I mean, it's pretty straightforward in that that was how we set it up, right? That they're in different clauses. So setting if you set it and they're not they're consistent, they're not negations of each other. So if you set this one such that it's true over here, then you're not going to run into problems with anything else that you are connected to. That if there is a satisfying assignment, then there's going to be at least one clause or its negation that is true in each one literal that's true or its negation in each clause. That means that by definition of this drawing of the edges here, they're going to necessarily be connected in the graph itself. Okay. If you want the full proof, of course, it's in the lecture notes. But what I want to do is show something a little bit more substantial. That's our first example. Let's look at another example. Right? Given, in fact, we've got independent sets and let's see. Okay. And yeah, let's go with vertex cover. All right. There we go. So hopefully you remember vertex cover from your midterm, I believe. So given a graph G and an integer k, does there exist a vertex cover of size k? So again, let's go ahead and go back over here to the visualization. If I have, say, a graph, there we go, like this. I'll just keep it like this. I need to select a vertex cover. So in other words, I'm selecting select a subset of vertices that cover all edges. Right? So for example, I could say I'll select this vertex and then this vertex and then this vertex. What edges have I covered? Well, all the edges that come out of those vertices, right? And this one and that one, right? But I have left this edge here uncovered. Look at its two endpoints. Neither one of those are in the set that I selected here. So I would necessarily have to select at least one more, and I've got a vertex cover here of size 4. Can you do better? Generally, you want a minimum vertex cover because you can always just select every vertex and cover all edges trivially. So our optimization version here is that we want the smallest size vertex cover. The example of the decision version of this is, given a k, does there exist a vertex cover of size k? Right? So does there exist a vertex cover of size 4? The answer is yes. Does there exist a vertex cover of size 3 here? I don't know. Help me out. Let me go ahead and redraw that graph. There we go. And then this one is hanging off over there. Well, I didn't. If I were being greedy about this, and greedy solutions don't generally work, but why would I select this vertex when I could have selected this vertex immediately? This vertex is only ever covering one edge, but this vertex over here is covering 3 edges. So let's try that. That's covered. That's covered. In fact, 4 edges because I missed that one, right? I still need to cover this edge, and this edge. And I can do that, but I can cover 2 of them by selecting that vertex, and those 2 are covered. And now all I need to do is select one more, this one or this one, and I've got my vertex cover. And so the answer is again yes. Yeah. And yes, of course, there's a vertex cover of size 4, right? Can you do even better? Well, in this particular example, no. You can't come up with a vertex cover of size 2 for this particular graph. But the problem is, given a graph, and an integer k, does there exist a vertex cover of size k? Right? And let me go back over here. And what we're going to do is we're going to reduce. All right. Here, let me go ahead and put this into the notes so that you have it. A vertex cover is a set of vertices such that every edge has at least one endpoint in V prime. It covers all of the edges. So what we're going to do is we're going to reduce from the problem that we just looked at, the click, right? So our I'm just giving that to you basically. All right, that's what we're going to reduce from. Right? So where are we? Good, good. All right, so let's go through our 5-step process here. 1, we need to show that vertex cover is in NP. Right? Not that we're showing that it's an NP complete, but as a first step, we need to show that it's actually in the set. All right, so let's go ahead and go back over to the overhead here. And let's go ahead and come up with a non-deterministic polynomial time algorithm that decides the vertex cover. So vertex cover. So my input, again, is a graph, v comma e, and an integer k. Right? And our output will be yes, except if G has a vertex cover, VC, of size k. Right? So again, 2 phases here. Guess. We'll guess a solution. Guess a subset of vertices, just like we did before. V of, here, sorry. We'll call it C, or VC. Let's go with VC. Of the vertices of size k. Clearly, immediately, this is going to be order n at most, because of course you could have an input at most n. You could select all the vertices if you want, but you can't select more vertices than there are. So it's at most order n, right? And it's non-deterministic. All right, verify. So for each edge E, and I'll call its endpoints U and V, in here, I'll just use mathematical notation here in E, we need to make sure that that edge is covered by a vertex in the vertex cover. If U is not in the vertex cover, and U is not in the V in the vertex cover, then reject. There is an edge that is not covered by either endpoint in this guessed vertex cover. Otherwise, if we get through all that, we accept. Right? Again, this is going to be order n squared. Why? Well, it's order m. The maximum number of edges here. This runs for each time. We're just asking whether or not something's in the set. This could be order 1 right here. And then this is order m, the number of edges, and the number of edges is bound by n squared. Right? So step 1 done. We've shown that this vertex cover is in NP. Okay. 2, we're going to select a known NP complete problem. To reduce from, and for us that's simply going to be the click problem, because I gave it to you, right? Generally, if you were to take a grad level course here, you would just be given, here's a problem, go ahead and reduce it, something, your choice, player's choice. Here we're going to go ahead and I'm giving it to you so that it makes it a little bit more, and in all of your assignments or exercises, you're generally given the NP complete problem to reduce from. So look at the structure of that problem and how you can exploit that structure to show this proof. Right? 3, we need to come up with a reduction from an instance of click to an instance of vertex cover. All right, and so here's my mapping. Right? So I'm going to use the Langle-Wrangle notation here. And an input to the click problem is going to be a graph, G, but also an integer, K. Right? And that's going to have a click of size K if and only if the resulting graph is going to have a vertex cover of some other size. Okay, so my reduction here, yeah, here we go. My right arrow. I'm going to map that to another encoding of another graph, and in this case, it's going to be the complement graph, and n minus k instead of k. Come on. There we go. It's just taking forever. I don't know why. We're not to 4 yet here. Right? So how is this reduction going to work? Well, I mean, it is what it is, right? How do you take the complement graph? You just take the same set of vertices. All the edges that were in the original graph, those become those are thrown out, and all the edges that were not in the original graph, those become edges in the resulting graph. We did this when we looked at graph algorithms before. We looked at the we looked at the transpose graph there. Sorry, where we reversed everything. So let's go ahead and take a look at a quick example here. And I'm going to use the example from my notes. So let's go ahead and draw a graph here. I'll give myself some more room over here. A, B, C, doesn't matter what the labels are, D, E, F, G. All right. Now let's go ahead and connect it. There's a square over here, and then there's a complete subgraph of size 4 here, and then A is connected over here. All right. If this is G, what does G complement look like? Again, it's the same vertex set, A, B, C, D, E, F, and G. But if I have an edge over here, I will not have that edge over here. If I didn't have an edge over here, for example, A to D, I will have that edge over here. So A is connected to B and C, so we will not connect that over here, but we will connect it to the other 4 vertices. Nice, pretty picture here. B is connected to A, C, D, and E, so B will end up being connected to F and G, and it's kind of symmetric intentionally, so I'll go ahead and do the same thing for C. D is connected to, again, B, C, E, and F, so we would end up connecting it to A and G over here, but we already connected it to A when we took care of that. So let's just go ahead and connect it to G. Likewise with E, it's going to connect to F. It's already connected to A. And then F, I think I've got everything at this point, right? F is connected to D and G, and so it would end up being connected to, in the complement graph, it would end up being connected to B, done, A, C, and E. Yep, we took care of everything already. So this is the complement graph. My observations here. The vertex set in G is equal to the vertex set in G prime, or in G overline here, the G complement. The size of it, right? What about the number of edges? How many edges are there over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 edges over here in the first graph. In the edge complement set, we do denote that with the overline there. How many edges are there? That's 1, 2, there are 4, 5, 6, 7, 8. In fact, I don't want to count them up here. I don't like counting. Let's think about this. In a complete graph on 7 vertices, we have 7 choose 2 edges, which is equal to, I'm going to have to pull up Wolfram Alpha here. Seven choose 2. That's going to end up being 21. Right? Again, it's going to be 7 factorial over 5 factorial, 2 factorial, which is equal to, these all cancel out, and in the numerator, you're only left with 7 times 6. 2 factorial is 2, so those cancel out, and you've got 21. Right? I could have done it. I'm just proving that I can do it, right? Without Wolfram Alpha. But 21, right? So why is that number important? Well, if there are 11 edges in the original graph, and there are potentially 21 edges total, then all I need to do is say that there are 10 edges over here. And you can go ahead and go through and verify that over here. Because if I take the union of a graph and its complement, then I'm basically producing a complete graph of size size 7 over here. Now, why is that important? Because my reduction here is going to exploit that fact. My reduction is going to say, suppose that there's a click over here of size k. Right? That preview here, there it is, of size 4. Then that means that there's going to be a vertex cover over here of size 4, n minus k. Or in this case, it's going to be 7 minus 4. 7 minus 4 is equal to 3. I'm going to be able to find a vertex cover over here of size 3. How? Okay. Well, here's the preview of how it works. I'll highlight these things here. All right. Highlight. There we go. So here's my click of size 4. Right. Now, what is my vertex cover over here? It's everything that's not in the click. There we go. So those three things together will cover all of the vertices. And you can see that it's covering these 4 vertices over here. It's covering twice now a couple of these vertices. Edges, excuse me. Edge, it's covering this edge. It's covering that edge, covering that edge, that edge, that edge, that edge. And there are no other edges that are uncovered. Right? So how do we go about proving that? In other words, my claim is going to be, so we need to prove it, step 4, that G has a vertex, G is a click of size k, if and only if G complement has a vertex cover of size n minus k. There's my mapping right there. Right. Make sure that everything's still working over here on YouTube. All right. That's my claim. I need to prove it. Proof. Here's the proof idea, and then we'll go into it in a little bit more detail. Okay? Forget about those particular examples, but here's the idea. Here's G. All right? I'll draw it as a cloud of vertices and whatever. I'm not going to be too specific about it. But here's a click within G. Right? And suppose that C is of size k. Okay? When we map this over here to G complement, that set is the same. Right? And everything over here is all the vertices without C. I'm going to call that my vertex cover. Right? Because that's what it is. All right. Every vertex over here. So again, this is my here we go. This is my click, and this is my vertex cover. Everything outside. Just like I highlighted before. I need to show that this is indeed a vertex cover. Right? That all the vertices in here cover every edge in the entire graph. So there are a couple of cases, and here's the idea. There are a couple of cases. Suppose that my edge lies completely within this blue region right here. Right? It's covered, right? Because both of its endpoints are within that vertex cover. Okay? What if an edge lies with one endpoint over here and another endpoint over here in the click? Right? That's still covered. Right? Because you only need one endpoint to cover an edge. And you don't necessarily need two. Now, the only case that we have to take care of here is what happens when we've got an edge within this where both of its endpoints are within this set right here. I'm going to argue that that's not possible, right? This is an edge in the complement graph. By way of construction, that would not be an let me go ahead and call that E. that would not be in the original graph. Therefore, I would have two vertices in my supposed clique that are not connected to each other. Right? And so that's basically the argument right there. That this is not possible. It either has to lie completely outside over here, or one of the endpoints has to be in your vertex cover, and the other one is in the non-vertex cover, C. But it is not the case that both of those endpoints are over here in your non-vertex cover C. Okay? So let's be more formal about that. Again, my claim is that G has a vertex cover, or sorry, clique of size K if and only if G complement has a vertex cover of size n minus k. Okay? All right. I'm going to prove both ways here. Again, if you've got an if and only if, that's both arrows there. So I'm going to go ahead and prove one way. I'm going to let C be a clique in G of size k. All right. Let E, and I'll give it a name, and its endpoints names U and V, be an edge. Sorry. In G complement. In other words, E is in the complement edge set. Okay? So that starts our series of implications. Oops. E is this edge here, and that's going to be an edge in the complement graph. This implies, by definition of what a complement graph is that edge is not in the original graph E, or in the original edge set E. Right? That implies that either U is not in C, or V is not in C. There we go. Or both. Again, that is a possibility. That implies that U is in the set V minus C, or it's in the set V is in the set V minus C. Right? There we go. Which means that UV is covered by either U or V or both. That implies that, and because I was general about this, I just said let this be an edge. This is the edge in the complement graph. It's got to be covered somehow. This implies that V, the set of all vertices, but you take out this supposed clique, is a vertex cover in G complement. Right? What's its size? Well, the size of V is n. The size of C by our setup here is k. And so, consequently, the size of V minus C is n minus k. Because they are disjoints. We're taking out all those elements. So if we start out with n, we take out k of them, then how many do we have left? N minus k. Now here's a really cool proof here going the other way. Basically, we need to show, suppose, that VC is a vertex cover in G complement of size n minus k. All right? We need to show that V minus VC is a clique in the original graph G. Right? I'm showing the other way now. So what is the definition of a vertex cover? Let's just use logic. For all U and V, for all vertices, all vertex pairs, UV is in the complement edge set, implies that U is covered, or V is covered. V covers the edge, right? So again, let's walk through this. For all vertex pairs, U and V, if UV is an edge in the complement graph, then it needs to be covered, right? So let me actually annotate these things. If UV is an edge in G complement, it needs to be covered. ... That implies that U covers UV, or V covers UV. Right? Again, that's my premise. Suppose VC is a vertex cover, and so that's just by definition. Okay. Now let's consider the consider the contrapositive. Right? Remember the contrapositive? P implies Q is equivalent to the negation of the conclusion, implying the negation of the premise. So in this case, let me go ahead and copy this and go to another slide. I'll be very, very careful not to get this stuff. Copy. All right. Paste. There we go. I can get rid of that stuff really quick here. The red annotations. There we go. All right. So there's the definition of VC. VC is a vertex cover. Is equivalent to this logical definition right here. Now I'll annotate this. This is the premise. This is the implication, and this entire thing is the conclusion. So let's go ahead and state the contrapositive and understand what it means. For all U and V, the contrapositives do not change the quantified statement, but I will take Q and I will put it down here, but I will negate it immediately. So in other words, this gets negated, this gets negated. What happens to disjunctions when they get negated? They become conjunctions. So U is not in VC, and U is, or V is not in VC, implies, now I'll take P and put it over here, but I will take its negation. So immediately if I take a negation, UV is not in the complement edge set, that not cancels out, and I have that UV is in the original graph's edge set. Okay? Now again, let's interpret this logic right here. If neither U nor V is in VC, then they are connected. Right? So all you have to do is take all such U's and V, and they form a clique of size K. Because we started out with the assumption that VC here is a vertex cover of size n minus k, right? N minus k, yeah, right here. Then if we take everything that is not in that vertex cover, that neither one of those is in the vertex cover, so we take everything else, UV, then they must necessarily be connected by an edge, and that forms a clique for all those pairs. And the size of that is, of course, K. Pretty cool. All right. Okay. Oh, and then finally, step 5, of course. I'll do a hand wavy version of step 5 here. We just have to show that that mapping 5, the mapping is computable in deterministic polynomial time. Right? How? Well, if you've got a graph and a vertex set and an edge set, all you have to do is dump the vertex set, iterate over all possible edges. If it's in the original graph, then don't include it. If it's not in the original graph, then include it, or at most order n squared. Right? Or if you take a matrix representation, all you have to do is go through and flip all the zeros to ones, all the ones to zeros, and you're done. Mapping k to n minus k, that's a constant time. So at most order n squared, and it's all deterministic. Okay. Okay, that kind of concludes everything that I generally cover in this course. So going forward here, with only 2 days left, tomorrow, of course, we'll have our review. No new material tomorrow. We will do our review like we've done before. I will pull out the final exam from the last couple of years. We'll do as many as we can in 1 hour as practice. Then on Thursday, I will not be having a live stream. Instead, I'll have extended office hours through Zoom, just like we did for the midterm. Feel free to come and ask questions. But of course, your final exam will be released on that day in the morning, in the morning at midnight, 1 minute past midnight. You'll have 24 hours to complete it and submit it through Canvas. It'll generally all be written, so don't worry about programming on that. But of course, you do have your final assignment. Remember that there is 50 points bonus available on that if you want to do all of the exercises, or you can do some subset of the exercises. Regardless, it's worth 200 points. There are 250 points possible. We graded out of 200 points, and that will be the conclusion of this 5-week course of Computer Science 3. We hope to have everything graded by Monday, maybe Tuesday at the latest. But of course, grades are due pretty early, I think by the 19th or something like that, the 18th or 19th, certainly before classes start in the fall, which 20, 21, 22, 23rd, August 23rd. Thank you for joining me on this like that's 10th time that I've done this course during the summer. It's only about the 3rd time that I've done it online or in a hybrid mode. So hopefully it's down pat a little bit here. If you are if you have colleagues or friends that are taking 310 in the fall, note that there are 3 different sections. As of like 2 weeks ago, I am teaching one of them. I'm teaching CSCE 310H. That's the honors section. So if you, there are only 9 people in it so far. We want to keep it small. But if you do have colleagues that might that think that they're up to the challenge, go ahead and have them contact me. Otherwise, there are 2 other sections. I don't know what mode they're going to be offered in. In fact, I don't know what mode anything is going to be offered in this fall. But I can tell you for sure, my course will of course be in a hybrid mode as usual. It's not an online course. I will be lecturing live in the classroom with a mask, and everybody would be expected to have a mask as well. But it'll also be live streamed over YouTube. So let me know if you have any questions. I don't see any questions from those that are watching right now. If you, otherwise, I'll see you in office hours, and we'll have our review tomorrow. Okay. All right. Have a good day, and I might see you in office hours.